Fantastic. Great. Thanks, Shafi, for that introduction. It's great to be back at Berkeley and get to talk a little bit about some of the work that's going on. And so I'm going to talk today about safety-critical autonomous systems and say a little bit about that. I'm at Caltech, but also visiting the Simons Institute. Is the Simons Institute for the theory of computing or of the theory of computing? Dick should tell us. Is it for the theory? For. All right, fantastic. I've got it right. Okay, good. I didn't have to do any real-time changes to my slides. Okay, so what are the types of systems that I want to talk about today? Well, these are systems that we all trust and believe will sort of perform correctly, and if they don't, bad things happen. So for example, Aircrafter 1, so I flew in this morning on Southwest, so I thought I'd give them a heads up. And if we can turn the wash lights off, that would probably be useful, just so we can see things a little bit better. And of course, we fly on these systems every day, and we trust that when we get on a plane, we're going to get to where we go and that nothing bad's going to happen, and that works, right? And so it's certainly a safety-critical control system. When these things go bad, something bad happens. Of course, you know, for many of us, especially here in the San Francisco area, another upcoming safety-critical control system are autonomous cars. And so these are running around right now, usually with safety drivers, right? But eventually people are talking about they're going to run around without safety drivers. And so we need to think about, you know, well, how are they going to work and what's going to happen, et cetera. And so I'll talk a little bit about that. Thanks, Claire. So I put up here one from Autonomy because I have no affiliation with Autonomy, but 3 of my students work there. So I figure, you know, they may be doing something that relates to things that I'm doing, even though they won't tell me about it. But there are lots of other types of safety-critical control systems. For example, to some extent, the power grid is a safety-critical control system, just in the sense that if it were to go down and go down at the wrong time and go down for too long, right, this would cause major problems, I think, here. We changed the lights just so we could see the slides a little bit better.
But I can't
see me?
You,
all right.
I can't see you now, sorry.
You want to change them? Okay, so they'll reset those. So this is another one, and one of the things that, you know, all of these have in common is they are all examples of safety-critical real-time decision-making systems, the topic of our particular program that's going on at the Simons Institute and that I'm part of. And so I want to talk a little bit about these, and for me, part of the motivation, and those of you who see me speak before have heard me talk some about this, was the DARPA Grand Challenge that happened back in 2004 to 2007, which Caltech participated in with a bunch of undergraduates. The Caltech undergraduates built this vehicle. They built several. This is Alice. Actually, the first vehicle was Bob. This is Alice. And so Alice is an autonomous vehicle originally built for off-road driving, although we also used it for urban driving. It was built by 75 Caltech undergraduates from scratch in about a year and a half. And so it kind of shows you what can be done back in this was sort of circa 2006 was probably when this picture was taken. It consists of lots of sensing, lots of computing, lots of communications, all integrated together, lots of different programs running in a very complicated setting. And it is the precursor, or one of the precursors, to what we see now today. Many of the DARPA Grand Challenge veterans and alumni are the people who are sitting in the self-driving car companies and getting all of these things to work and kind of bringing that experience with them. So if you kind of look inside Alice, what you would see would be a bunch of modules that are running on computers. Each of these little boxes, don't worry if you can read the words, represents some function that's being carried out, either some type of sensing or navigation or decision making or other things, all connected together, all working, all running across 30 cores or so worth of computing and carrying out all of these computations. And this is very similar to what the architectures that you would see in today's self-driving cars that are driving around downtown San Francisco and other places. And so they all have a very kind of a similar setup. Lots of different computation running now on much more advanced CPUs and other things, but still basically the same ideas. And I think what amazed me back at the time that we were doing this is that all of this can actually work. We actually know enough about how to get these to run. And so this is an example of what Alice looked like as it was driving along. So you're seeing it driving in an intersection, coming up to that intersection, waiting until it's its turn, so it has to sense those other vehicles, determine that, okay, it's now its turn to go. It goes through the intersection. It doesn't know exactly where things are, so it has to localize, figure out where the lane lines are and other things. It has no prior map, so this is back before these things were kind of mapped in exquisite detail. That was not part of the rules, so you see it kind of veering around a little bit as it tries to figure out what's going on. Comes up to another intersection, stops a fair distance behind, that's set by the rules, waits until it's its turn to go. As soon as that car goes through, it says, great, I can now pull up to the intersection, stop at the stop line. So it comes up to the intersection, it knows the other car was there first, waits until it goes through, and then it goes through the intersection, right? So all of this is running with nobody in the car, right? Having to figure out where all the lane lines are, where all the other cars are, sensing everything around it and doing real-time decision making about how to make all of those things happen. And so in that particular spot, you saw it doing some relatively simple maneuvers. Certainly all of us could do that if we were driving a car. But now, of course, doing that all autonomously and working more or less correctly, right? I mean, you can improve the performance and other things, but basically did what it was supposed to do. But it didn't always do the right thing. Here's another same time. This is from the DARPA Grand Challenge in 2007, where it's trying to go through an intersection. There's cars coming both ways. You can see it kind of hesitates going forward. It starts going forward. It stops. It backs up in the middle of the intersection and then starts to make a turn very hesitantly. Cars are coming up. They're honking at us. Hey, get out of the way. What the hell are you doing, right? So we come in, finally, right, sort of get in the lane and start driving, right? People freak out a little bit about, sort of where we are, right? They see a, 3-ton truck coming at them and they sort of go, I'm not sure I want to do that, right? So what happened, right? That's probably not very safe behavior, right? And if there had been pedestrians and other things and that type of an error had happened, you can imagine somebody might have gotten hurt. And so what's very interesting is that what happened there, in fact, if you kind of go over to this diagram, and you say, well, something went wrong. There was a bug someplace. And in fact, the bug was that there were inconsistent assumptions between two different layers of abstraction, right? Where a higher layer thought one thing was going on and a lower layer thought something else was going on, and they got inconsistent and it got confused. And I'll explain a little bit more what those layers are and what was going on. But essentially, we missed it. Right? We did lots of driving, we did lots of testing, we did lots of simulations, right? But there was this one condition that we'd never seen before that somehow caused the system to get confused, right? And of course, in a safety critical control system, that's what you're worried about, that one condition in a million, right? That's going to happen, and you got to simulate a lot, right, in order to get that condition, and you may never get it. Right? And so that was the type of thing we were looking at. And to me, at that time, that really motivated thinking about, well, how in the world are we going to design these sort of complex systems and get them to work? So how do we design systems of this complexity? How do we make sure they function as they're desired? So let me generalize that a little bit and just talk about kind of safety critical autonomous systems, mainly autonomous vehicles, but as I said, the power grid and other things might be there. And I think one question we should ask is, how safe is safe? Right? How safe do we need things to be? And so, for example, we can look at what some of the statistics are on safety in the current systems that we have. So vehicles, human-driven vehicles, the safety record for human-driven vehicles is about 7 deaths for every billion miles driven. Right? So that's about what a human can do right now. Traffic deaths due to an accident or something like that, either of the people in the car or people around the car. So that seems maybe pretty safe, right? Nobody here drives a billion miles, right? So 100 million miles, right? You would kill less than one person. But there are a lot of miles driven, right? So in the United States, that turns out to be 35,000 traffic deaths per year, just in the US, right? Because there are that many miles driven. And that's certainly way too many, right? Leading cause of death, in some sense, up there on the list of things that kill people. So are there safer ways? Well, you can look at what happens in train and rail types of systems, so something like the San Francisco Metro as an example. So buses and trains turn out to be about 20 times safer. So 0.1 to 0.4 deaths per billion miles driven. And so, really quite a lot safer than driving yourself. But the safest mode of transportation, maybe not too surprisingly, since this is the one we hear the least about people getting hurt in, is in fact air transportation. And the statistics there are 0.07 deaths per billion miles. It's 100 times safer for me to fly from Pasadena up to Berkeley than it is for me to drive that same distance. Right? So if you have to choose and you want to go down to LA or you want to come up to San Francisco, you should fly if you're worried about your safety, right? Because it's 100 times safer to do that. And these statistics come from this paper. It's a little bit dated now, but kind of goes through all of those things. And this is in the United States, so this is sort of US data. So I think we can ask a couple of things about that. So, how is it that in the aerospace system, aerospace industry, we're able to make things so safe, right? What's going on there, right? And so, I think there are a couple of things. So one is that there are very strong certification requirements. So you can't just put software in an airplane and try it out. You actually have to go through a certification process. That certification process, there are many of them, but one of them is called DO-178C. And DO-178C establishes how safe as an engineer you have to guarantee your software is, or demonstrate that your software is before you're allowed to put it out in use by the public. And there are a variety of levels of safety. And so there's hazard classes and what's the software level for that, and the number of failures per flight hour. Catastrophic failure means possible loss of human life. So that's the software does something and the plane might actually crash. And for level A software, where the failure of that software could lead to a catastrophic error, what you have to demonstrate is you will have no more than one failure in every billion hours of operation. right? So a billion hours of operation turns out to be 100,000 years. Right? So every 100,000 years, your software is allowed to have a bug that trips. Right? So that's pretty damn safe. But that's what you have to demonstrate. And so there are a variety of processes for doing that. And so this DO-178C has a lot of, how do you actually demonstrate that? What type of analysis do you have to do? All of those things. So part of the reason that aircraft systems are so safe is that there's strong regulations around those that force the engineers designing them. And many of these were, of course, things developed by the industry, right? Because you obviously want airline safety to be something that the public can trust. And so that's kind of where we've ended up on that. But there are other things, of course, that make the air traffic system particularly safe. For example, it's a very structured operating environment. You have air traffic control and other things that are moving things around. You have very well-trained personnel. There's a pilot, right, who gets hours of training, many hundreds of hours of training probably every year in addition to flying and getting certified and all of those things. And you have very expensive vehicles, right? Airplanes are not cheap. They're maybe on order $1 million per passenger, right? And so you can do a lot, right? And I'll tell you some about what some of those things are. I think if we now think about, okay, good, so it's possible to design these systems that are that safe. We've demonstrated we can build them that safe. How might we do that in the automotive industry? Can we get to that level of safety? So at the component level, things are actually pretty good. Your car components don't break in a way that causes death very often. Most deaths are caused, right, due to the humans driving them, right, making a mistake, not, due to your engine going out or your tire going out or, right, or something going out inside your car. Sometimes, but not that often. If you start thinking about autonomous vehicles, right now a lot of the backup stuff, right, that happens when you have a failure is the human, right? Oh, my tire went out, I need to pull over to the side of the road, right? Oh, my engine stalled, right, I need to figure out a safe path, all of those things. So as we start doing that in autonomous vehicles, at the vehicle level, we're going to have to be a little bit more fault tolerant, right? Most of the autonomous cars that are out there driving right now are designed to drive when all four wheels are inflated and the engine's running and the brakes are working and the transmission's working and the communication systems are working and the networks are working and the computers are working, right, and all of that stuff. And so we're going to have to say, okay, what if that's not all the case, right? Your aircraft can run on one engine, actually they run on 0 engines, right, for a little while. And so, they've thought about how do you run in fault conditions, right? Not how do you just sort of say, okay, it's a fault condition, I give up, everybody's dead, right? Or it's a fault condition, pilot, figure it out, right? The aircraft can actually still continue to operate. And of course, I think the hardest thing that we're going to see in automotive systems is at the system level. Right? So when you're around people and it's in a mixed environment and all of that stuff is going on, right? And so that's going to be the really hard problem where I think we have very hard challenges. Okay, so these are the types of things that I've been thinking about, for the last couple of years, in some sense motivated by the DARPA Grand Challenge, but increasingly for me, it's been more on the aerospace side that we've applied some of the ideas that I want to tell you about. So what I want to tell you about today is a little bit of that. So I'm going to start by telling you more about the aerospace systems and how are things done there and what are some of the challenges, even in aerospace systems, that we're working on. And I'll say a little bit, not particularly deep, but try and give you a little bit of a sense about some of the ideas mathematically and in control theory, which is my field, and how do you do that, right? What are the tools we can apply? What are the various techniques? And it's a very nice combination of ideas that are coming from computer science and controls and many other disciplines. And then at the end of the talk, I'll try and kind of come back to self-driving cars and talk a little bit about, can these be applied? Should they be applied? How might they be applied? What does that look like? Because this is an area that's changing very rapidly, right? So since 2007, right, there have been dozens of companies that have come out that are now building these cars. And I'd just like to point out that a lot of the work I'm going to talk about today is in fact tied to things going on here at Berkeley. And in particular, a lot of the aerospace stuff is stuff that we did as part of the iSci-Fi project that was done with Edward Lee and Alberto Sangiovanni-Ventitelli. And a lot of the self-driving car work is stuff that we've just started in the last year or so with Sanjit and Claire and Rujna, Shankar Sastry, Tom Griffiths, and Bjorn Hartman here at Berkeley. And so this is very much joint work with many people around here. Okay, so let me start. I'll say a little bit about aerospace systems and try and give you some insights there about that industry, and then say a little bit about kind of the mathematics and control theory behind this, and then come back to the self-driving case. Okay, so how do we design complex aerospace systems? And we use a model-based development process. That's what the kind of current industry standard is, so that's MBD. And traditionally in an aerospace system, you'd have a design V, right? So you would sort of start and say, okay, well, I want to start at the system level. I'm going to design the aircraft. How big should the wings be? What should the range be, et cetera? And then I'm going to take this down to the subsystem level. I've got an electric power subsystem, a propulsion subsystem, a hydraulic subsystem. And then I'm going to eventually go down to the component level. I've got gears and valves and transformers and other things. And so I'm going to flow everything down, and then I'm going to put it all back together and verify it as I go back up, right? So I'm going to take all my specs at the system level. Those are going to translate to specs at the subsystem level. Those are going to translate to specs at the component level. I'm going to design the components. I'm going to put them together. I'm going to test to make sure the components satisfy their specs, put them back together, make sure the subsystem satisfies the specs, put it together, make sure that the system satisfies the specs. And that has worked very well in the aerospace industry for a long time, and was sort of developed when things were relatively simple. And so, for example, for the electric power system for an aircraft, which is one of the systems I'll talk about, this is a typical electric power system for a, say, 737 era aircraft. I think this is actually maybe a 757 era aircraft, where you have an electric power system. There are generators on the engines that are generating electrical power. Those are powering up buses that the loads are connected to. The loads are the various flight control computers, the various actuators, and other things. And so you have maybe a couple of different buses. So the blue things in the middle there are AC buses. You might have some transformer units that transform those to lower power or DC, depending on what you're doing. And you've got, 2 engines, a backup generator on each engine, just a backup generator just in case the primary generator fails, maybe some battery backup, an auxiliary power unit, right? Some redundancy built in there. And it's relatively easy to make sure that this system, right, will operate in faults. If one engine goes out, you'll still have electrical power, right? You've got a similar problem with propulsion, right? Do I have enough propulsion to, take off and land and other things? But just on the electrical power side, you have to worry about that too. It gets more complicated when you try and get more efficient. The problem with this system is that you're basically carrying around 2 to 3 times the amount of power generation capability that you need to make sure that it's always there, right? And as you start looking at it and try and optimize and get your airplane to be more fuel efficient, that means lighter weight, right? And get it, to sort of be lower cost, that means less components, et cetera. You start saying things like, well, do I really need a left backup generator and a right backup generator, right? And do I need each one of those to be able to power up the entire aircraft, for example, right? Maybe I can say, look, there are 4 or 5 or 6. The battery, let's say there's a battery backup, an APU, left 2 generators, right 2 generators. Can't I assume that 3 of the 6 of those are running and make sure that no matter which of the 3 of the 6 of those are running, they have enough power, right? And if that happens, right, that the likelihood that 3 of them fail is less than 1 in 10 to the 9 flight hours, right? I ought to be able to get away with that. Right? But now the problem is that it depends which 3, right, and how things are connected up. And so I start having to worry about how do I route power in more sophisticated ways because I don't know what's going to be up and down. And so you get a more complex system to do that. So this is what the electric power system looks like for something like the 787 aircraft. You may remember when the 787 was coming out, they had some problems with the electric power system. You probably heard about it in terms of the lithium batteries, right, and other things. That's what that system looks roughly like. Those little kind of oval-like things are the buses. There are now a lot more buses. There were maybe 4 buses on the system when I was looking at before, right? I don't know, it was 1, 2, 3, 4, 5, 6, 7, 8, 9, and it was probably a half dozen or a dozen buses on this system. Lots of different redundant paths. You see lots of arrows connecting these. Why? Because we need to be able to route power no matter what happens. So these systems have gotten more complex as we've tried to make them higher performance, lower cost, higher availability, lower weight, right? All of these sort of design challenges. And this is very much a software-controlled system because now all of the contactors that say route power this way are all controlled by a microprocessor someplace that's saying, oh, right, this engine just went out, so now I need to reconnect the power and reflow it in order to make sure that the right stuff gets the right power. And so the challenge with these complex systems in the aerospace industry, what are they struggling with? They can build systems that are as safe as they are, but it is very expensive to do so. And part of the reason it's very expensive is that you discover changes downstream. So this is a plot of the number of design changes requested as a function of time. So on the horizontal axis, you're looking at the amount of time going by, and then on the vertical axis, you're looking at the number of change requests coming through. And what you see is that early in the design process, there are not very many change requests, but late in the design process, like when you're testing things, there are a lot of change requests coming through. So they're discovering the problems with their design late in the design stage. And that's very expensive, right? Because now you've already built the thing, you've already sized all the components, you've already done, you're partway back up that V, right? And so it's getting very complicated, right, to change things and go back and do everything. So that's the challenge in the aerospace industry is these things are too expensive, right? And time consuming, and they get delivered late. And you hear this, right, with all of the aircraft that come out, right, that it's, over budget, over time, right? This is cutting into the business, et cetera. And so in the aerospace industry, people have thought about, well, how do we do better? And one of the ways we can maybe do better is to use models in a better way. And to try and do more upfront. So take this design V, and instead of waiting until we're going back up the sort of design V to discover problems, try and do more on the front end. Do little verification loops. Let's make sure that everything works. Let's have tighter specifications and other things. Let's use formal methods and other ideas that I'll talk about earlier in that design process. And can we, by doing that sort of thing, shift this curve so that maybe we get the same number of change requests. Maybe we sort of take that as a constant, right? We're doing a design, we're gonna get things wrong, but can we shift it so that those change requests, the area is the same, but they come earlier in the design phase when it's cheaper? And so this is where the aerospace industry is going, is how do we pull up, right, those changes so that we can discover them earlier when we're still doing stuff on paper ideally, right, or in simulation, right, or in very early prototyping rigs rather than on a full aircraft. And so that's kind of where things are going. The difficulty is this is hard, and there's more research needed to figure out how to do that. And so there's a lot of things that people are trying to figure out how to do, verification of these sorts of things, et cetera. And I'll talk more about these. But model-based synthesis is one of the things people are doing. So we need to design with downstream verification in mind. We need to think about going from a design then verify sort of a mentality to more of a specify then synthesize type of mentality. And I'll talk more about that in a second. Now, just to sort of show how some of these things all play out, I kind of give you an example. So when you look at a modern aircraft, it's got a lot of subsystems. So if you sort of peel away the skin, not only do you see the seats and everything else, but there's wiring running all over, and there's hydraulic pumps all over the place, and there's sort of cables and everything else, and we've got these kind of tight design specifications. And as I already mentioned, for the catastrophic failure, so for anything software controlled where the software going bad could lead to loss of life, we have 100,000 years that we have to demonstrate. And just in the US, there's about 30,000 flights a day. Turns out to be on order 10 to the 8th flight hours per year. And so if you kind of look at the world, there ought to be maybe one every year or two software problems that lead to planes crashing. And that's about what happens, right? Every year or two you hear about that Air France flight, right, or that Air Malaysia flight or whatever, right, that sort of went down and we don't know quite why. And it might have been part of the software, right? So that's kind of the level that we're at. So we really are pretty much at that level. And if you think about, what is it that these systems have to do to maintain that level? So let me kind of take this example that I showed you of the 787 power bus, or something like the 787 power bus. So what you're seeing here is across the top are the sources of power, and you see that you have 2 generators on the left engine, 2 generators on the right engine, a left auxiliary power unit, a right auxiliary power unit. There are batteries that are in here that are sort of not shown. There are high voltage AC buses, low voltage AC buses. Why? For efficiency, right? Because now you don't want everything running off high voltage AC. Some things will run more efficiently off low voltage, so you put more buses in. There are high voltage DC, low voltage DC. Why? For efficiency. There are transformer units. But look at all the paths between all of those things, right? There are lots of different ways of powering them up. And so what happens in the software that's running this is that in normal operation, you would say, well, everything's sort of functional, so I want to use the most efficient way of routing power. And so you might say, okay, well, I'll power up, right? My left and right generators are running, and so I'll power up all of the buses, those are the rectangular, long rectangular things, in some way. And so I've sort of highlighted the paths of power that are being used, and so everything should be getting power from something, although I think that the middle buses there are unpowered somehow. Anyway, sorry about that. And now you say, great, so now that's the normal operation, but we know that these generators aren't going to run for 100,000 years without failing, right? I mean, you're going to do maintenance on them, et cetera, but at some point one of them's going to fail. And so what do we do when, for example, that fails? Well, when that fails, right, then the buses that were getting supplied by that can no longer supply power, and so we need to reroute that power. So the first thing that happens is that we lose power on all of those buses because that was what was getting driven, let's say, off of that particular bus, and we need to repower them. So the natural thing you might think of is, oh, well, that's no problem, right? You can see there's buses that are powered up right next to them. Let's just connect them, right? Now, you can't quite do that because on an aircraft, the engines are not spinning synchronously, right? So in the electric power, the terrestrial electric power system, all of the generators are all synchronous. They're all connected together. But in an aircraft, those engines are not phased with each other. And so if you connect them together and that right engine is still running, right, and the generator just isn't quite working right, you can suddenly get 2 electrical signals that are connected together out of phase, and that can lead to huge currents and high temperatures and fires and other things. So you can't do that. So you actually have to disconnect first the buses that are powering up the old stuff. So the first thing you have to do is disconnect that, and now once they're disconnected, then you can reconnect them via some other path. Right? And so there's a logical sequence of things that have to happen and a set of constraints on what that logical sequence can do. And the software has to solve that problem. And that's, you got to worry about, I just showed you the right engine failing. What if a different engine fails? What if while the right engine is failing, another engine fails, right? Because if you're in a bad storm or something. So you can imagine, right, there are all of these complicated possibilities, and that's why it's so complicated to go test all of these things. And this, of course, is something that, as I'm describing it to you, is very much happening in some sense at a logical level, as you can imagine, right? You know, sort of tools from formal methods and verification and other things could be used here. But there's also dynamics that are going on underneath these things and temporal constraints, right, to repower things, et cetera, et cetera. And so it's complicated. And DO-178C provides ways of doing that, right? And in the kind of latest version, it allows for the use of things like formal methods, model-based development, et cetera, to do that. Having said all of that, it can still be a challenge. And so I'll give you an example of some of where that challenge can be seen. And this is in a test flight for the 787, basically the system I've been showing you. It's called ZA002. The flight number there is a test flight. This happened back about 7 years ago, 8 years ago now, maybe 7 years and a little bit, and on the 787. And so this is an article, and you can see the title, Official Word from Boeing, 787 Dreamliner Fire and Smoke Details. Okay, that's not good. Right, fire and smoke in an aircraft, right? You know, not what you want. So, you know, you can't read the text here, so I'll pull out a little bit of it. What it says is that there was a loss of primary electrical power. Okay, well, what does that mean? Okay, primary electrical power is the thing that powers the aircraft, right? So really what happened is that the cockpit, right, lost power. You're looking at a bunch of computer displays and they go off, okay? You are now in a plane flying, right? This was actually a plane coming in for a landing, so it's probably at 10, 15,000 feet, right? It's coming in for a landing and all of a sudden, all of the cockpit displays go off. Right? And all of the computers that allow, right, the stick and rudder and other things to control something have also gone off. That's what happens when primary electrical power goes off. Not good. So first off, that should never have happened, right? That should be a 1 in, all right, sort of 10 to the 9th flight hours thing. This is a test flight, right? Sort of what in the world went on. Okay, so something went wrong and something didn't happen. But engineers are really careful about things, right? And so, in fact, if you keep reading, what it says is that the RAM air turbine, the RAT, deployed and allowed a safe landing. Okay, so chances are, unless you've heard me talk before or you're in the aerospace industry, you have no idea what a RAT is. So the RAM air turbine is something that is underneath virtually every commercial aircraft. It is, there's a picture pointing to it. You can barely see it down there, so let me blow it up a little bit. It looks like this. It's basically mounted up underneath the fuselage, and it's set up so that if you lose primary electrical power or primary hydraulic power, right, then this thing will automatically drop down into the airflow. There's a prop on the front of it that starts spinning. That prop does two things. It spins up an electric generator and it spins up a hydraulic pump. Those go to completely separate circuits that power up the flight control computers and the primary flight actuators. Right? So some engineer someplace said, yeah, but what if the software doesn't work? Right? If the software doesn't work, I want to have a whole separate redundant circuit, right? That's how you get, right, that 1 in a billion sort of case in there, right? And so that RAT deployed as they're coming in, basically within, I don't know, 30 seconds or something like that, everything comes back up, right? So they had to fly kind of open loop, really open loop for 30 seconds, and then everything comes back up, and then they've got only what they need to land the plane, right? So they land the plane safely, right? And you didn't hear about people dying or other things, right? Because that safety system came in. So that's an example of the types of things that our engineers are doing. Just to give you a sense of all of this, part of the reason you never heard of these RAM air turbines is they are very rarely used. So there are about 100,000 flights a day globally. That means 35 million flights per year. I was able to find 6 documented RAT deployments where somebody wrote an article saying here was a RAT deployment, right? Now, not all of them are going to get published, right? So maybe there were 10 times that many, right? That would be about 3 per year on 35 million flights. So 1 in every 10 million flights, right, this RAT will deploy, right? How do you verify that that's right, sort of do the right thing in all the right conditions, et cetera, et cetera? Right? So I've actually been to the manufacturing floor where they build these things. They actually have a poster for every time the RAT deployed, and they have the number of people whose lives were saved, right, because their system deployed. Because if their system hadn't deployed, that plane wouldn't have had any power and would have crashed. Right? So that's the type of thing I think that when you think about safety critical systems, you want to think that's the sort of mentality you want to have, right? Like no matter what happens, we've got a way to get out of that thing, right? So that's the type of thing that's going on. Okay, so with that, that's sort of how aerospace deals with this thing and a little bit of the mentality of those things. Let me tell you some about where aerospace is going and the types of things that people are trying to do. So when you look at the systems that control these, so the control systems, the software systems that control all these systems, a fairly typical scenario will be something like this. And people who were at the boot camp last week, you saw this diagram. We've got some physical system, the plane in this case, your autonomous vehicle, whatever it is. You have some sensors and actuators down on that bottom level. And then you have a variety of software loops. So at the next level loop up, you have this sensor processing. It's probably some Kalman filters that are doing GPS and other types of things. Some feedback controllers keeping you in the lane or keeping you sort of on your flight path or whatever it is. You have at a higher level, some optimization, trajectory optimization, other types of energy optimization, optimizing the sequence of things that are going to get turned on and off perhaps in that electric power system. And at the highest level, you have some decision-making logic that might be saying, okay, we are in a fault mode, or we are in some mode in which we need to discard some of our goals or other things. And so these multi-layer hierarchies are common. It's very important when you're designing the system to think about the environment. The environment means the external things that might affect your operation. And often, as a controls person, we think about the environment affecting just the physical system, winds and other things in the context of this. But in fact, that environment is really represented through all of the layers of the abstraction, right? Because those faults can be things that have an implication all the way at the decision-making level, but also increasingly, if you think about something like autonomous vehicles, that external environment is not just your system and the external things that might happen to it, but the people around you, the other cars around you, right? A very complicated system. And at the decision-making level, do I turn left or right, go through the intersection, et cetera? It depends on that environment. Now, the other thing that's happening is that increasingly, these are systems that are networked systems. So there's some sort of networking and communication that connects all of these together. And that allows a much more intricate set of interactions between the different layers of the abstraction. And so we can do things that are more complicated. We can put a lot more computation on. So often these sort of blocks, which are similar to the blocks I showed you for the block diagram for Alice, might be things where we have multiple blocks that are running at different, for solving different special cases, at different sub-layers of abstraction within these layers, right? Various different things. And as we do that, then we have to worry about the fact that it's a distributed system now, a multiprocessor system. So we have clocks on all of those things. They may not all be synchronized. So we might have events that get seen in different orders in different places, depending on when they get the message, right? And so we have to deal with all of that stuff. Another thing that happens is increasingly the system model that's sort of at the center is used in the design stage, but increasingly as we think about online learning and other things, that system model is something that gets used at the operational stage. We actually query that model and say, if I turn left, what will happen? Or what's the maximum speed I can go, or other things. So again, that complicates the set of interactions that are going on. And then, of course, as soon as you put a network on things, then people say, oh, let's talk to the cloud, let's talk to the operators, let's get other subsystems. This is in some sense like just the electric power system. There's a hydraulic system, there's a flight control system, there's a landing gear system, right? All of that stuff too. And so we have to think about, how do we manage all of this complexity? And so we can do that, of course, in the usual ways that we've learned from places like computer science. We do it via abstraction. So we can say there are layers of abstraction, and I want to separate those layers so that some set of engineers are going to worry about what happens at that lower physical layer, and then another group at the kind of control layer, and another group at the optimization layer, and another group at the decision-making layer. We often also decompose this when you go look at teams that are working on this. You'll have the sensors guys over on the left, right, and the controls guys, right, or the hardware actuator guys over on the right, the optimization people, et cetera. And so these are all ways that we divide this problem up. And I'll tell you that my own experience has been that that's where most of the errors occur, right, is between these layers. That the assumptions that people make, right, on the two sides. Remember, I told you that was the problem that went wrong in Alice, right, when it backed up in the middle intersection, was there was an inconsistency in the way that two different teams were thinking about the problem, right? And so, same thing, the sensor guys think one thing's going on, right, the optimization guys think a different thing's going on, and we kind of don't get it right. So, but nonetheless, that's how we design these systems. And one of the ways that we can kind of try and combat that is to use contracts. I'll say more about what those are, but assume guarantee contracts specifically. Okay, so that's the type of thing. We also have to worry about not only vertical layers of abstraction and vertical contracts that connect sort of the different layers, but also horizontal contracts. So now I've put these little arrows in there. As we distribute these systems, right, then we have to know how are the other agents going to behave, right, if it's a multi-car system or something like that. Okay, and so one of the things we've been doing and trying to get the aerospace industry and increasingly the autonomous car industry use is to get more formal about use of verification and synthesis in both model and data-driven simulation and testing. Okay, so there are lots of systems that this sort of picture shows up in. Aerospace systems is one, self-driving cars is another, factory automation, process control looks something like this, smart building, smart grid, right, smart transportation systems, mobility, right, things that we're looking at in this real-time decision-making program very much look like that. And there are lots of challenges around all of this. So how do we define the layers and the interfaces? So the vertical contracts. How do we scale to many devices? So things like Internet of Things or mobility systems, that's the horizontal contracts. And how do we keep in mind all of the properties that we care about? Stability, robustness, security, privacy, all of those things. So it's a nice, rich space in which we can think about what can be done. So I want to just say a little about specifications, because that's one of the things that we've been putting a lot of time on. And when you think about the specification, you have a bunch of properties over here on the left. These are things that you sort of write down. You say, these are the properties I'd like to be true. We like to think about breaking that down into a contract, something that is implementable and has an assumed guarantee framework. We usually write that in temporal logic or some other formal mathematical language. And that allows us to then implement things on the components such that when we synthesize something that satisfies the individual contracts and we compose them, we know it works correctly together. And so that's a way to think about it. And kind of pictorially, you can think about you've got some global property. You want to break things up into this component should satisfy this set of sub-properties, a contract. This one should set these. And when I compose these two things, I get a combined behavior that sits inside my global set of properties, right? So somehow the composition, they constrain each other, right? So that when working together, they give you something that works correctly. And if you do that right, it gives you some flexibility because it essentially gives you modularity. That is, if I have component A and I know that component A satisfies its properties and component B satisfies its property, I know when I compose them that that subsystem will satisfy the intersection of those properties, and then the subsystems, when intersected, will satisfy that. And now you can go and change component A or component B as long as you satisfy your contract, right? And so different companies can do things in different ways and come up with new innovations, but those contracts are going to make sure when you plug it in, it works the right way. Okay, so those are the sorts of things that we'd like to look at. And this assumed guarantee form, that is where we assume that the contracts are under some assumption on the environment and what inputs I get. I'm going to give you a set of guarantees on my performance, can then be nested together. So you want that, for example, if I've got 3 components, then the guarantees provided by component 2 and 3 should imply the assumptions that component 1 is making. And similarly, the guarantees from 1 and 3 should imply the assumptions that component 2 is making, right? So that when you put it all together, right, the guarantees that one set provides sit within the assumptions, right, that I made in providing my guarantees, right, and the circularity all works. So that's the type of thing you'd like to do. Okay, so, and again, these contracts, these assumed guarantee contracts can be vertical between layers, or they can be horizontal between elements within the same layer in a distributed system. And so one of the things we think about is how do you synthesize these and do other things. Okay, so once you have contracts, then you can think about how do we check these contracts. And so for the computer scientists, you'll know that model checking is one way to do that. So if I have here something at just the discrete layer of abstraction, but you can make similar claims at other levels, I might have some finite state machine that represents my decision-making logic. I might have some formula here written in linear temporal logic. Don't worry if you don't know that. And there are great tools coming from computer science that allow us to take the system description and the property and basically go through and say, yes, for all possible executions of this system, the specifications will be satisfied. Right? And so they will basically formally verify. And what's important here is they will verify that with different interleavings on a distributed system. Right? So if one system operates slightly before the other, or a clock tick happens or something like that, they check all possible interleavings. Very important, because in these distributed systems, right, that's where things go wrong. But the other powerful thing they do is that they will give you a counterexample if it doesn't work. Say, no, this specification is not satisfied, and here's a counterexample. Why is that important? Because engineers always think they got it right, right? And they never believe you. And then you go, no, but think about this, right? What happens if, right? And then you give them what happened, right, in that ZA002 flight. And they go, oh, yeah, crap, if that happens, the entire primary power system could go down, right? Okay, you'd like to figure that out ahead of time, right? Rather than by flying it and figuring out the hard way. And now that plane was, right, you know, sort of a production-ready plane almost, right? Since final certification, they'd go back and do it. So it's really important that those tools and techniques work. Okay, so model checkers are getting much, much better. They can check all possible execution traces. They can look at environmental actions, so you get models of what the environment can do, et cetera. If you've not used these, then I would encourage you to learn something about them. There are lots of modern model checkers that are out there. We tend to use SPIN and TLC at Caltech. They can handle many, many states. And the goal is that we'd like to leverage these somehow for doing control. So this is an existing technology, but I think that the kind of principles of this technology have not been realized at all the layers of abstraction. So how do we do that style of model checking within the trajectory optimization layer or within the kind of feedback control layer? I think the other thing we can do is think about sort of turning that around a little bit. And so if we say, look, I've got a system model, I've got some set of assumptions, the description of the environment, for example, I've got some set of requirements, that gives me a model of what the system environment can do and some set of formal specifications. And in verification, we design some finite state machine that implements that decision-making logic, and then we verify that either, yes, this set of properties is satisfied for this environment with this decision-making logic, and so I give you basically a certificate saying, yes, you're okay, or I give you a counterexample. But the other thing you can do, of course, is flip this around and say, well, geez, if I give you the system model and give you the formal specifications, why not just synthesize the controller that does that? Right? I've told you, here's what the system is, and here's what I want you to do. Can't I write a program that sort of, goes and says, fine, here's the logic for how to switch on and off, right, the electric power system so that you never short two things together and blah, 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 blah. And in fact, you can do that, and that's called synthesis, and you can do that in kind of standard computer science settings. This has been known for a while. In control settings, there's some things that make that hard, but sort of doable. And so this is sort of where we've been heading, is to do these sorts of synthesis tools. And so I'll just very briefly tell you about kind of some of the synthesis tools before I sort of hop back to autonomous vehicles. So we're interested in what's called reactive protocol synthesis. And so the diagram might look something like this. We're just at the decision-making layer, that top layer. It's all discrete, just for simplicity. I've got some process here that's the process that I'm controlling, the aircraft, and I can turn on or off certain switches, connect certain buses together, right, if it's the electric power system. I've got some environment, and that environment's also discrete. A contactor can fail, a sensor can fail, a generator can fail, right? All of those would be things that my environment can do to me. And that may depend on my system state. In other words, it may be that the contactors that fail are the ones that are open or closed or something like that, right? More likely than something else. And so my environment, you can think of being interacting with that. And now the controller process, right, the decision-making process, gets to look at, right, sort of what the current state of the process is, and in this version of things, we'll allow it to look at what the current state of the environment is, so we'll assume that that's known or can be inferred very quickly. And then what we'd like to do is to satisfy some specification along the lines of what I wrote down. And generally speaking, this is hard to do for general classes of specifications. So in the context of linear temporal logic, a certain class of specifications, it turns out it's doubly exponentially hard in the size of the specification. So if I have 5 specifications, right, then it will take 2 to the 5th, so that's 32 times, it'll take 2 to the 2 to the 5th, so 2 to the 32nd nanoseconds to do. That's a long time. But if I double that, and I have 10 specifications, right, it will take 2 to the 2 to the 10th, that's 2 to the 1,000, right? I worked that out, that's 10 to the 300 years, right, something like that, right? So that's like age of the universe, right? So, right, that's not going to happen. So way too complex, and that's kind of stopped us. But it turns out that there's a special class of specifications called GR1 for general reactivity specifications, in which we assume basically this arrow up here that we can measure what the environment's going to do, and that allows us to kind of unwind the system. So I can say the environment makes a decision based on the current system state, and then my controller gets to know what the environment's going to do and knows what the process state is, and then makes a decision, and then we implement that, and then I come back and the environment. So it's like a Stackelberg game if you do game theory, right? Sort of you're breaking the symmetry, right? If you do that, it turns out, if you do that, that's one, and you look at a special class of specifications, these GR1 specifications, what do they look like? In linear temporal logic, they look something like this, so let me not worry you too much about it, but they basically say I have a set of safety assumptions and a set of progress assumptions. So the safety assumptions are never do the following thing, and the progress assumptions are always eventually do something over and over and over again. And if I assume that my environment has safety and progress assumptions, then I should imply that my system has safety and progress specifications. So if I assume the environment does something of this form, then I need to guarantee that the system does something in that form. That problem turns out to be much simpler, and in fact, it's only cubic in the number of states. That's pretty good, right? Doubly exponential to cubic. Now, cubic in the number of states versus doubly exponential in the size of the system specification, it's actually an exponential factor in there. So the states to represent a system spec can be exponential in the size of the spec, but usually aren't. And so it is often the case, right, no guarantees, but that it's a reasonable number of states. And so we've been able to go and kind of pick up these tools that came out of work by Pitterman, Punwelly, and Saar from 2006 and apply them in many of these control situations. So again, GR1 are these general reactivity formulas, and they fit within this assumed guarantee framework. That is, I might use this for, the assumptions could be my higher level of abstraction assuming something about my lower level of abstraction, or my lower level assuming something about the higher level, or it could be me assuming something about the environment, right? All of that kind of fits. Okay, so let me just very quickly kind of give you an example of how these synthesis things work. Why does this work? So I'm going to do this runner-blocker game that Punwelly came up with. The idea is I've got a runner. The runner can either be in this position on the left, in the top, the bottom, and the goal is to get to the right. The blocker can be in one of three positions, either at the top, the middle, or the bottom. And the idea is that the runner and the blocker should never be in the same position. So the runner is trying to get over here, and the blocker is trying to block. And of course, you can imagine that if the blocker stays in the middle forever, right, then there's kind of nothing I can do, right? Because if I move up, the blocker could move up and run into me, right? And so what am I going to do about that, et cetera? So we have to assume something about the blocker. We're going to assume the blocker always has to move, right? So now, of course, what's going to happen? If the blocker moves down, I'm going to move up, and then I'm going to get through, right? If the blocker moves up, I'm going to move down, and I'm always going to get through, right? So under the assumption that the blocker always moves, seems like there should be a strategy. So how would we find that strategy automatically? Well, if we enumerate all of the possible states, so here was the starting state, right? And then what I'm doing is I'm listing all the possible system states, and there are transitions between those states, right? Where the red is the blocker making a move and the blue is the runner making a move. Then there's a transition map or a graph that connects all of these states together. And what the way to solve these problems is to say, well, let's look at the winning state. That's the thing down here at the bottom. These are losing states. We want to never end up there. So let's assume that we started in the winning state, and let's ask the question, from what initial states, if the environment took some action, I could take some action so that I end up in that winning state, right? So that's a question that you can ask. And in this particular case, you would say, well, if I start in any one of these two states, there's only one thing that the blocker can do, right? Move down here or move up here. And when it moves, I move over into the right-hand side and I win. So now I can say from any one of these states, I'm winning. And now I can ask the question again, from what set of states, right? If the environment takes some move, I can find a counter move that always gets me to the goal. And of course, if you do that, you end up with this. And of course, now here what happens is, right, if the environment goes this way, right, then I have two choices, but I'm going to go down. So if the environment moves up, I'm going to move down. I'm not going to, right, move to the other spot because then I would run into the blocker. So now we can just keep iterating this until we get to a fixed point, until we get no new states. And we can say that's the maximal set of states from which we can converge, we can find a path down to the winning state. And if that includes my set of initial conditions, right, then I win. I can win this problem. And we can back out a strategy from that, right? Essentially, if I start up here, I need to get into the next set. If I start in here, I need to do the next set, right? So you can back out a strategy. So that's how these techniques work, and you can show that that can be done with cubic complexity. Okay, so we can apply those types of systems. So for example, if I go back to this electric power system, you can write down the requirements. So here's a bunch of them, right? No AC bus shall be simultaneously powered by more than one AC source, right? That was the thing that I told you. Buses should be powered according to priority tables, right? So maybe you've got, certain things are more efficient than other things. Not unpowered for more than 50 milliseconds, right? So you've got all these things. And the spec that I was showing you before was implementing these. And we've got some environmental descriptions about how often can things fail, right, and what types of things can fail. And when we put all of those together, we can essentially formulate this as a GR1 synthesis problem and formulate the logic that allows us to, well, we can first just write down the specs, and you give me a solution, and we can verify that, in fact, that works under all possible interleavings. And in fact, this can be done, and you can go and show that the failure that occurred, right, in the ZA002 flight would be caught. Right? That we say, oh yeah, what about this sequence of events? But also, you can synthesize, right, that logic automatically. And that synthesis is particularly useful if you're trying to do design space exploration. What topology should I use? But that topology depends on whether I can synthesize a control law, right, a decision-making law, and I want to do that automatically, right, not by hand. Okay, so now let me just in the last 5 minutes come back and talk a little bit about how might all of this, or how do we think about sort of self-driving cars. So, in fact, there are a couple of interesting consumer applications where I think these ideas can come to play. So one is self-driving cars, and I always like to point out to people think of these as new, but they're not that new. Right? In the 1980s, Ernst Stickmans was driving self-driving cars around in Germany, and CMU was doing things right at the NAV lab. This is one of the early cars that Dickmans had, right? It was a big van with cameras on and other things, and he was driving it, well, the team was driving it on the Autobahn. Here in California, but in particular at Berkeley and many other places, right, the PATH project was doing autonomy. This is probably down on the 405 freeway or something, heading down towards San Diego, where they were doing platooning and other sorts of things. The DARPA Grand Challenge I already told you about, right, that came around in the 2000s, 20 years, right, after some of this stuff was already being done. And in the DARPA Grand Challenge, there were a lot of teams. Again, these are the alumni who came through and do things, and I already kind of showed you some of the things that happened there. It was really only recently that everybody started getting involved, right? And so now we're starting to see things, and new techniques are being applied, right? So, exquisite mapping of the environment is a standard thing that they do to simplify the problem. Lots of machine learning and other things to classify the obstacles. Those didn't exist so much back in the early days. Much more sophisticated optimization and control because you could do more computing. So I think the challenge in this area, of course, is how do we go from 7 deaths per billion miles to something like 0.07, and are we there yet, and can we do it? And I'll say a little bit more about that. Consumer drones are another interesting one, right? Again, drones go way back, right? Sort of, 80 years. The more modern things that we see, things like Predator, Global Hawk, the military drones that are there. I was on a study that the Air Force Scientific Advisory Board did where we believed in 2000 that the pilot was optional for most missions that the Air Force flies. And things like the DJI Phantom. So Zhesheng Li, who's an alum here from Berkeley, is the chairman of the board of DJI, and one of his master's students at Hong Kong University of Science and Technology, Frank Wang, is the CEO. So very much has a connection back here to Berkeley. They really build on a lot of the advances. And what people are talking about doing is package delivery, swarms, personal transport, safety critical stuff. Right? Because if you're delivering that, sort of Amazon package above the city of Berkeley and that thing falls out of the sky, you got to worry about what happens. So I think there are interesting things to think about there, and people are starting to put funding in there. It's also interesting to just look at what that ecosystem looks like. So there are people working on processors for autonomous vehicles, right? So all of the NVIDIA and others that you hear about are working on specialized processors. There are people working on sensors for doing that, cameras, laser range generators, radar, et cetera. There are people working on connectivity because this wants to be cloud connected and other things. There are people working on the mapping tools for doing this. There are people working on algorithms to actually implement the planning and optimization and other things. There are people working on the security and safety associated with all of this, the development tools for associated with all of this, and all of this is happening, and then there are people actually making self-driving cars. So this is what that industry looks like. It's pretty crowded, right? It's pretty interesting as an area. I think there are a lot of challenges in how we kind of deal with all of this. And this is actually a slide that I put up in 2016. I gave a talk in this room. And so I'm going to put it up again because I think there's still the right challenges. There are things we've solved, and there's things that are still work to be done. I think that we basically solved the problem of driving on city streets with normal traffic and everybody obeying the rules. That's solvable. Autonomous cars can do that today. I think we have yet to solve driving in crowded and unstructured environments where people may or may not believe, sort of pay attention to the rules. And so why? Well, because you have to predict what's going on. You have to understand. When you're in a parking lot, what are the rules of the road in a parking lot exactly? Right? Or when you're on a road that's been blocked and you're making a U-turn in the middle on purpose. Yeah, that's right. That's the most expensive car. Kamishkar's car has right-of-way automatically, right? Whether it's the most expensive or not. So, right, yeah, less expensive just because it's the one willing to take the damage, right? I think the other thing is that getting accident rates that are on par with humans, right? 1 death in every 10 deaths in every billion miles, 1 death in every 100 million miles. I think that's doable now. The deaths are going to be weirder. You're going to say, why in the world did the autonomous car do that, right? But it's going to get rid of a lot of the stupid things that people do, like paying attention to your cell phone instead of what's going on around you, right? So it'll be different, right? But I think we can probably do that. The question is that good enough? Is society going to tolerate that? And my usual argument here is, right, that if 1% of the fleet were autonomous cars, 1% of the cars in the US were autonomous cars, so we go forward 5 years, right, or 3 years, 1%, and we're just this safe, right? Then what does that mean? That means that we're going to get, if it's the same rate, right, it was 35,000 deaths, right, per year in the US. That means we're going to get 350 deaths per year from autonomous cars. That means every day you're going to pick up the San Francisco Chronicle, right, or the New York Times, or the Washington Post, and it's going to say, autonomous car kills child in Michigan, right? And the next day you're going to pick it up and say, autonomous car kills, elderly person in Florida, right? And then as a society, I think we're going to say, ban autonomous cars. They are killing people, right? Now, they're not killing people any more frequently than people are killing people, right? But our engineered systems have to be better. So I think we can do this. I just personally don't think it's going to be good enough. Right? So you can decide, what you think. But I think getting 10 to 100x better safety, that's an open problem. That's well beyond the mean time between failure of the parts. So for example, you have to operate in the presence of failures, right? You have to operate with flat tires. You have to operate with engines going out. You have to operate with your sensors going nuts, all of that stuff. I think that we can do things where 99% of the miles completed are done in self-driving mode. We see that already. That's different than saying 99% of the trips are completed, right? Because there's a lot, the hard parts that occur on a trip, right? And that's what you care about as a consumer. I get into the autonomous Uber and I get there 99% of the time, right? I don't care that 99 out of 100 miles. I mean, I've probably been 100 miles in Uber cars, right, in the last month. Right? And so, if every month I've got an Uber car that breaks down and then I got to do something, that's a problem, right? So you really want 99% of the trips, right? Because I haven't taken 100 trips, right? I've taken 20, probably 10 trips, right? Okay, so again, I think that that's going to be hard, and in particular with humans. I think using machine learning to improve performance, absolutely, right? Classification, prediction, all of those things. I think using machine learning to guarantee safety, harder problem, not solved. I don't know how we do that one. So, it's really hard to learn these rare events, right? 1 in every 10 million flights, right, is going to have that rat go down. Where's your learning algorithm that's going to learn what to do on that type of a sparse data set? It's not a frequent event, right? So maybe we have to combine it with formal methods and other things. All right, last one. I think that it's going to be relatively easy to have 1 to 2% of the cars self-driving with humans as a backup, where we allow accidents to happen at the same rate. Right? So humans as a backup. I think the really challenging part is going to be when 20 to 80% of the cars are self-driving. Most but not all, or many but not all. Right? It actually, I think, gets easier when 100% of the cars are self-driving. Right? Because now you can make assumptions about what the other cars are going to do that are pretty common. The 1 to 2%, you can kind of tolerate it, and the human backups there. I think the middle is actually going to be hard. So I think it's easier after that, but probably not. Okay, so I've gone a little bit long. Let me stop there. I hope I told you about aerospace systems and a little bit about some of the ways that people in aerospace think about what's going on. I've told you a little bit about some of the formalism that people are using, or our group's using, and others are using to try and manage the complexity of these systems. And I've said a little bit about self-driving cars and what needs to be done there in order to really move forward. So with that, I will stop, and thank you for your attention. I'm happy to take questions. Thanks. Yeah, in the back.
What's the basis of the claim that the problem can be solved now? At least reaching human level of safety. So given the fact that 1 in like 7 billion, this includes all the world, including the dangers of including fog, country roads, snow, ice, and so on.
Yeah, no, that's a good point. So maybe the way I should rephrase that. Yep.
Somebody calculated that it requires driving about 4 billion miles, randomly selected and so on, show that there's like 20% improvement. What's the basis?
Yeah, so I mean, it's, there's no formal basis for it. I'm making it up and just claiming, right? So, but here's what I would say about it. I think that one of the things autonomous cars can do is to say, I'm not qualified to drive in these conditions, and I won't. Right? So it's snowy outside, and I'm not qualified to drive in snow. By the way, people are driving in snow, right? So Autonomy tests in Boston, they drive in snow all the time. People drive in rain. People drive in all sorts of, they drive on dirt roads, right? All of that, in some sense, you can start layering all those things in. But what I think they will say is, this situation, I don't have a map, right? Or my connectivity's gone down, or too many of my processors have failed. I think they will stop. And so that's part of how we'll get there. Now, we may not tolerate that as consumers, right? Because, well, I get in this thing and it just says I can't go, right? So, but, just even, I would say, even when we were doing the DARPA Grand Challenge, right, 10 years ago, I was convinced at that time that, we could drive pretty safely, right, with that vehicle at that time, right? And again, if one of our processors failed and it mattered, we would simply pull it over to the side of the road and stop. So I think that's, just, again, it's not anything rigorous. Now, if you want to do more rigorous, go look at the statistics being generated by Cruise, which is a branch of GM, or Google and others, and ask, what's their current mean time between disengagements, right? And, is that converging towards something that, right, would be consistent with my conjecture? Sort of. So some of them publish, some of them don't. So in California, if you're testing in California, at the least you have to publish whenever a disengagement occurs, right? You have to actually report that disengagement, or an accident occurs, sorry. And you have to report the number of disengagements you had and other things. And in particular, both Google sort of a little bit before Waymo, but Waymo to some extent, used to put out monthly reports on here's sort of our, how many miles we drove and how many disengagements and other things. And so some of that's available. And a lot of the stuff that gets reported, we've actually gone back in and looked at as part of some proposals and other things. So some of it's available, especially here in California where they have to disclose more. But if you're testing in Arizona, which is why a lot of the companies are testing there, then you don't have to disclose that. So we don't know as much. Yeah, Praveen. Yep.
Seems to be almost every week you hear of an accident. You conclude from what you said that they're not doing a good job.
Well, so I think, okay, so first off, I'd say the two cases are probably different because, of course, Tesla is deploying autopilot where you, the consumer, are the safety driver, whereas Cruise is testing with safety drivers. And I think what I would say is that in the case of Tesla, the point of view they've taken is this is not an autonomous system, right? This is a autopilot, right, that you were supposed to pay attention to. And then when people don't pay attention, it's the driver's fault, right? But I've driven in a Tesla in autopilot, and we drove from San Francisco Airport to downtown San Francisco, and in my opinion, it made 2 errors that could have led to an accident if the driver had not intervened, right, in what, 15 miles, right? So that system is certainly not good enough to do well. I think Cruise and Waymo and Zoox and the other companies that are testing things, right, they're still trying to explore that space, right, and push the envelope of what they can do. And sometimes when they push that envelope, right, they make mistakes. They learn from those mistakes and other things. So I think they do know what they're doing, but they're trying to tease out what works and what doesn't work, right? I don't think Cruise, people may know better than I do. I don't think anybody has died in an autonomous vehicle crash yet. With the exception of the Tesla one where it drove underneath the truck, and we can argue whether that was autonomous or not. It was not supposed to be autonomous. They didn't build it that way. So that's what I would say. Yeah, well, again, accidents are going to happen, right? So, the one I like is, I don't remember what company it was, but whoever was doing this in Las Vegas, right? The first day they're doing this autonomous bus in Las Vegas, the first day is like within an hour of them starting this service, it ran into something, right? It ran into a delivery truck that was backing out, right? Because it didn't back up and the delivery truck expected to back out. Accidents are going to happen, right? And, in aircraft, shutdowns happen, other things happen, right? The thing doesn't happen, you don't fall out of the sky, right? But we all get delayed, we all have that problem happen. So I think that one wants to decide, I think accidents are okay. You want to minimize those. If there's no loss of life, it's a different category, right? So fender benders, I think, are still going to happen. Yeah.
There's a question about the role, perhaps changing the role of the person within systems like this. One curious, interesting fact was the fact for bus intelligence, where they're out on the same roads as
Yep.
all the individual. So is there sort of, in that case, is there a benefit to chauffeuring? It really reaches peak in the air system.
Yeah, that's what the pilot is, or in some sense.
National Aerospace. So going to the notion of assistance is the ideal of assisted driving is that you decide on point, you're at point A, you decide on point B, and then you just meet and deliver in between. Is there a more humane roll-off or a more reasonable roll-off of what assistance can be?
Yeah, I think it's an interesting question. So a piece of data that I don't have that I'd like to collect is if you look at taxi drivers, right? So, buses are big and people stay out of their way, et cetera. Taxi drivers just like any other car. Taxi's just like any other car in some sense. But you have a chauffeur, a person, right, whose job it is to do that and who's presumably paying attention and doing all the right stuff, and they're trained to do that. So that would be, maybe the epitome of what human driving could be, let's say, in a, comparable thing. I think it'd be interesting to look at what that is and say, is that a good enough target, right? Because maybe we can achieve that. I think this other question you asked about, are there ways to roll it off? So, for example, I think a problem that is very doable would be, I'm going to make it really, really simple. So let's suppose I say I'm going to have an autonomous car, and this autonomous car is going to run on an exact route, and it's going to stay in exactly one lane. And if something's in front of it, it's going to wait until that thing gets out from in front of it, and then it's going to drive through. And if somebody cuts in front of it, it's going to stop. And it looks a lot like a train, right? That is, it's on a track essentially, right? It's just that it's not a physical track, right? It's just a software track, right? And now, it's just like longitudinal control, right? All I got to do is make sure that I'm not going too fast forward, that I can't stop before somebody cuts in front of me. And that's a much easier problem, right? And I think there we could probably crank the rates way high. Now, the question is that valuable, right? Because that's no better than a bus, except that now if that was an individual car, I don't have to stop at all the intermediate bus stops to pick up and drop people off, right? I can but now I'm driving, instead of a bus that can hold 30 people, I'm driving 30 cars, right, that can drive individuals, so it's not a very efficient solution. So anyway, I do think there are backed off modes, right, in which we can get increased safety. And I think looking at, and then, people are talking about doing things like remotely, right? If it comes up on a situation where I can't move for more than 30 seconds, it phones home, right? And somebody comes in, sees all the cameras and says, okay, here's what you should do in that situation. Maybe that's the way we do it. Right? Yeah. I think the biggest challenge is that this requires getting very formal about what you're doing at all levels, right? And so within the aerospace industry, when you're spending $1 million a seat and you're spending, sort of billions of dollars, right, developing the aircraft, you will put years and years and years into developing the specifications, developing the simulation models, developing the prototyping, et cetera. I think if you're talking about autonomous vehicles, we're not going to spend $1 million per car developing these things, right? Or, well, billions of dollars to develop them and millions of dollars to put all the safety systems in them. So I think the challenge is, how do we take that point of view and get it to be applied in a system where the engineering effort, right, is going to be much different, and the regulatory environment is going to be much different, and the cost structure is going to be much different. The tools are also not quite there yet, right? For situations like, how do I maneuver around people and bicycles and pets and sort of other cars? That's much more complicated than how do I taxi down the runway and take off into the sky where I've got a lot of room around me, right? And the only other things around me are other air vehicles that are following the same rules, right? So I think, again, how do we reason about the environment around us? I think that's a big problem. How do we, once I've got some representation of the environment, how do I use that representation to prove in a formal way that I've got the levels of safety that whatever society ends up requiring? I think those are a couple. Okay, well with that, thank you again.